This is IAT355 Lecture 9.2, where we're continuing our discussion of trees, in particular doing NodeLink diagrams where we use a more advanced kinds of geometry to be able to address some of the space problems and also to deal with the issues of managing perceptual constancy, which comes up in the videos that we're about to show. Another approach that had been talked about a bit in the 90s, I'd like to show it partially to indicate that some of the times you get a great idea and, you really put your heart into it and make it work, but it might not be all that great in terms of actual functionality. So let me show this thing now. So the 3D approach I'm about to show you is called the ConeTree. And what it does is it adds a third dimension into which layout can go. And it's a compromise of top-down and centered techniques that we mentioned earlier, although the technique precedes space tree. It was done in the early 90s. And children of a node are laid out in a cylinder around a cylindrical region below the parent. And siblings live in one of the two-dimensional planes. And so what's going on here is that instead of laying things out in 2D, the hope with the technique of the ConeTree technique that I'm going to show is that we can use three-dimensional space to lay out all the stuff in the tree around what's nominally a greater amount of space, but that space gets projected onto the screen, and the way you interact with it is to move your viewpoint around and move the objects around. So, as I said, the technique is called ConeTree. It is an interactive tree viewer, and basically the way the thing works, I'll talk about it and then I'll show it, is that it, you click on a node, and if that node is not at the front, it moves it to the front. So this thing says SIGGRAPH. If I clicked on this, and it was actually an interactive item, that clicked on SIGGRAPH here, that node would move to the front. The parent nodes that are, responsible for it would also move to the front, rotating this thing and these things so that, the selected item and all its parents and grandparents all the way up to the root are towards the front in order to show you the structure. But the drawback, as you can imagine, is that when you're doing this, some of the stuff behind it is obscured and hidden by the fact that things are moving around. So let's show the demo for that.
This visualization, called the ConeTree, shows part of a Unix directory hierarchy. Each node is a directory. When a directory is selected, the tree rotates through the shortest path to bring the selected path to the front. The selected path is highlighted with the directory name. 3D is used to make more effective use of available screen space. A 2D layout of the same tree would not fit on the screen. The user would have to scroll through the 2D layout and wouldn't have a view of the whole tree. The 2D layout could be reduced to fit, but details would be lost. Interactive animation is used to shift some of the user's cognitive load to the human perceptual system. You can see this by looking at a selection done without animation. It takes several seconds to reassimilate the relationships between the parts. With animation, the perceptual system tracks the relationships because of object constancy. When the animation completes, no extra time is needed for reassimilation.
So one of the other points that Stu Card, who is doing the voiceover again, and you saw him he's the older guy in the Table Ends video. And so one of the points he makes that the space tree thing that we showed in the previous, the first video in this section, is that it's very important to not mess up the user's perception. It was a particularly salient point at the time that this was made because updating things and animating things rapidly, interactively, and quickly still was a heavy task for the computers of that era. These days is pretty standard. But it's still a very important thing to bear in mind if you want to maintain, help the user maintain a clear understanding of what's going on. If you're doing a large transition, take the steps with the transitions. And both of these techniques do that. The space tree thing, takes a three-step approach to dismissing old data, moving the space around to make moving the tree around to make new space, and then introducing the new sub hierarchy. ConeTree did something similar by carefully rotating all the stuff so that you could see it at the front. It rotated it all at once. Perhaps more smoothly would be to rotate it from top to bottom. But in their comparator that they showed in the video was, compare that to just instant transition, and it's very hard to understand. Okay. So here's another view of the same technique. This thing is a ConeTree that was implemented a number of years later. And it is in some ways an improvement, and in some ways not much of an improvement. And I'll just hide the video for my video for a sec so you can see it. And you can see this thing, that what it's done is giving you an oblique view, so that even though Excel is hiding a bunch of things, you have the chance to see each of the cone layers right here. So it's a little bit of an improvement. However, there are some ways in which the visual design choices don't help. This texture at the bottom here, the purpose of the texture is so that you can get a good sense of the curvature of it. I mean, it's flat, but you'd like to get a good sense of its smooth increase off into the distance, and also to be able to measure things visually by the distance between these diamond forms. The problem is that these diamond forms are very similar to these shadows. They're fake shadows. It's not really directly computed. It's just rebuilt on the basis of the horizontal extent of the cone here. But there's a shadow drawn and there's line segments drawn. So the cone tree is drawn twice, once in 3D up here and then once in 2D down here. But the problem is that the diamond shapes kind of get in the way of that. So anyway, it's an interesting looking technique, and the positive things is it might use a little bit more space, geometric space, to lay out the tree, but fundamentally, because most of the time almost all the time we're using 2D screens to be able to interact with information spaces, the kind of advantage that you get is a little bit limited, because you're projecting onto 2D. If you are able to hold the thing in your hands with some kind of virtual reality hand trackers or something like that, and turn it over and be able to investigate, that might help a bit. But typically for information visualization types tasks, you don't use devices like that. So these techniques are not necessarily so useful. It does also help use smooth animation to help the user, track smooth updates, and it looks cool. But the major drawback with a technique like this is occlusion obscures some nodes, and it requires a little bit of graphics horsepower, which these days is, everybody has. But at that time, it was, required special purpose computing when those things were first built. So an alternative solution to the problem of drawing trees is to change the geometry a bit. I'm not saying this is the only possible solution, but I'm just simply kind of giving illustrations of the way in which the design space of a NodeLink tree drawing has been explored. So what I'm going to show you now is something called the Hyperbolic Tree Viewer. And what that does is it applies a hyperbolic transformation to the space. And we'll show you what that means. Basically what it does is it expands the middle and shrinks the periphery. And also does something else which hasn't been done in the previous tree layouts, and that is it puts the root node, at the center of the drawing, at least to start with. And all the nodes expand radially from that center. So the root is at the center, all the subordinates, all the descendants are around it, and that idea is applied recursively. And as you get further and further out, presumably there's an equal distance between each node, but in the visualization, the distance is decreased so that when you get to the extremes, the node distances are very, very small, almost zero. And we'll show you what that looks like. So the concept is to put the root at the center, and with the nodes growing outward. If you were to draw it just like this, you'd have this little problem of any node looking like it could be the root. There's nothing to distinguish it. The hyperbolic tree technique I'm going to show you helps deal with that. So this hyperbolic browser is a focus plus context technique. We'll talk about that again later on in the term. And basically what that does is blend a detailed view with the stuff you're clicking your mouse on and staring straight at with a global view. So you first lay out the hierarchy on a hyperbolic plane. and then map that plane onto a disk, and then start with the tree's root at the center and use animation to navigate its representation in the plane. And so here's an example, a still picture of what that thing looks like. This is another technique that is animated. So here's what the layout looks like. Here's the root, and here are 3 child nodes, and so on and so forth. And as you can see, as the distance increases in terms of steps or descendant levels from the root, less and less space is allocated. And as you get closer and closer to the periphery, the size of the nodes goes from, reasonable, not great size text to just the nodes being drawn as dots to an accumulation of dots. In fact, the tree structures are shown here. Those are little trees that are the same size as this in terms of overall density, but a lot less space is allocated, and so therefore they're drawn smaller. So lay out the plane, lay out the hierarchy on the hyperbolic plane, and map this. And they had done a comparison with this to a standard 2D browser, comparing 100 nodes with 3 character strings, and they made a claim that they can show a lot more structure in this thing because the nodes are smaller and they're doing this spatial distortion. So we're going to show a demo of that in a second. Okay, so here's the video. It's also a YouTube video, but I'll play it now.
The Hyperbolic Tree browser is a focus plus context technique for browsing large hierarchies. Here we see a recent org chart of Xerox PARC containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as nodes approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail in that part of the org chart while maintaining the context of the whole. We can also grab a point in the space and drag it around as we like. To achieve crisp dragging and to keep transitions under 1 second, rendering of the tree is degraded in a couple of ways. Notice that the arcs are turned into straight lines and less of the exponential fringe is painted. The Hyperbolic Browser, like other focus plus context techniques, deals with the shortage of screen space by showing more about a few amidst a little about many. Here we use wafers to show the amount of space available for node information. Notice how nodes grow as they approach the center and shrink as they recede. We can interactively adjust how space is proportioned, say perhaps to introduce a sort of spatial socialism. The Hyperbolic Browser can support other types of hierarchical data sets, e.g. part assemblies. For some applications, an alternative layout works better. Here we have the children of the node in focus fanning out to the right. As a new node is clicked on, the structure rotates as necessary to orient that node's children to the right.
A particularly interesting application area of late is the World Wide Web. Here we see an overview of the Xerox web server with the Xerox homepage at the center and with linked pages displayed as children. By clicking near a node in this image map, a request is handled by a web server script which generates a new image with the new node centered. By clicking on a node, the web browser is directed to load the page represented. Of course, this constrains the user to the glacial interaction typical of the web. An alternate strategy is to use a sidecar helper app. We regain our nice crisp interaction even on this 4,000 plus node structure. However, the cost is that multiple versions for different platforms and/or web browsers have to be developed. A third alternative is to use Java to get both local interaction and platform independence in one fell swoop. The Java implementation of the Hyperbolic Browser can also be used to display arbitrary, hierarchical objects delivered through the web. For example, this is the PARC org chart again. This time we use thumbnail pictures on the nodes.
All right, so that was the Hyperbolic Tree browser. As you can see, that video was a creature of its times, as it were. That was made in 1995. The World Wide Web had started to become readily available in early 1994. This was in the era when NCSA, the producers of the Mosaic browser, which begat the Netscape browser, which you saw there, was actually every month producing lists, a little article that would grow by about that much text every week, lists of new organizations that had web browsers. So that's how small the web was and how slow it was at that time. So anyway, the idea there was, the technology was rapidly being developed at that time. In 1995 is when the Java browser had come along. But the indicator there that, of what the future looks like in terms of interactive visualization was kind of a prescient one, and the kinds of things that you're able to do now, sorry for the bump there, that you're going to be able to do now in Observable are the kinds of things that were envisioned a number of years ago about interactive visualization of other people's data on the web. But anyway, getting back to the hyperbolic tree, it's got a natural fisheye magnification in the center, and the layout depends only on 2 or 3 generations from the current node, and the rest of it is kind of approximated and shrunk down such that it doesn't dominate the layout of the rest of the space. It does smooth animations for change in focus and doesn't draw objects when they're far enough from the root in order to simplify the rendering and also to decrease the amount of complexity. So it's good for seeing local structure, but if you want to see the entire tree, once again, you're out of luck, or you just simply need more screen space. However, the problems with this thing are, when you're watching it, it does take a little bit of getting used to and reaccustoming your eyes as to where it is some of those nodes ended up, because there might be some rotational movement in addition to being just simply drawing things more towards the center and other things moving towards the periphery in kind of a nice linear fashion. When a node is moved, the children don't keep their relative orientation as they would in a Euclidean or rectangular space, and it's not as symmetric and regular as the Euclidean techniques that we showed first, and sometimes makes visual search more difficult. So the point is, with each of these visualization techniques, there are strengths and weaknesses of each of these approaches. And part of the problem is there's just too much data, and each of these techniques that we've shown, each of these visualizations that I've shown today, kind of indicate some of the trade-offs made and some of the other desirable things just sort of de-emphasized and not supported well. Hold on. So in review to what we've talked about with respect to trees and NodeLink diagrams, the tasks that we've been interested in supporting are to learn the structure of the hierarchy and to answer questions like who has the most descendants, what family tends to have the most children, who is a relative of whom, those kinds of questions. Following links is one of the primary things that you're going to do. Each of these visualizations supported that to some degree. So that concludes lecture 9.2, where we wrap up the discussion of drawing trees using NodeLink diagrams. Next, we'll start talking about space-filling representations, or the notion of enclosure, to represent something of interest in trees. In particular, what's being used there is the notion of that there's some spatial quantity that needs to be somehow represented. These preceding techniques have not addressed an issue like that.